2. You guys hear me in the back? I've been known to talk quietly. I need to be mic'd.
Mic check. All right, guys. Once again, if you're going to talk, please push yourselves over in the corner. If you're going to listen, please come and sit in the chairs or at least stand behind the camera. And we're going to get going.
Cool. Thanks, everyone. My name is Matt Maisel. I'm a data scientist at Cylance. And today I'm going to be talking about a malware similarity tool that uses nearest neighbor search methods. So during today's talk, I'll go through a motivation for malware similarity, how nearest neighbor methods could be useful for this particular task. We'll actually take a detour and go through a background of some theory and a brief literature review of nearest neighbor methods that are particularly interesting for our domain. And then, of course, talk about some related malware similarity systems that are out there that have been developed either in academia or out as open source tools. And then I'll get into the system design of a tool that I think addresses malware similarity using these methods, and go through the implementation of a tool called Rogers that will, it's actually up on GitHub right now. I'll have the link to it, and you can download it from the Python package index to test out locally. And then also briefly some experimental results from a small data set that I worked on. So motivation for malware similarity. As an analyst, search and retrieval of malware samples, it provides useful context during analysis. This helps us as analysts relate the context of previously analyzed samples that are well known and well understood, and basically take our unknowns from alerts or detections in various products or various SEMs or systems or logs, and if we have access to the binary, we can hash it, or we have some reference to it, we can basically look it up in this database or a corpus or an index. And I personally seen and personally developed when I worked at a SOC in the defense consulting industry, this database of basically hashes, and I think a lot of folks have done that. Maybe we've used fuzzy hashing as well too, but it would be great if we had a better kind of database or a better kind of index that represents the characteristics of samples that we want to query. And so that's kind of more for just relating context. So this in turn helps us prioritize samples for analysis. If they're unlike any sample we've ever seen in our corpus, we can prioritize that for more manual analysis or reverse engineering. Maybe we can also use it to route some of the samples to other tools and systems that are more expensive. Maybe there's a budget in terms of the API, number of API calls we can make, or maybe it takes time to detonate in a sandbox. So ultimately, if we have this index that kind of serves as a starting point pretty much for our analysis, we can easily use that to gauge and get some context around the sample we're looking at without having to look at it at all in more depth. So malware similarity then comes into play where, again, there's many different ways of doing this, but ultimately I think it's the comparison of either raw bytes, so looking at the binaries directly and comparing the raw bytes, or extracting static and dynamic features that really attempt to distill the characteristics, of what that sample. So, what it does, what capabilities it has, what functionality, and really then comparing those features, pairwise. So as an analyst, we can just extract the raw data and look at it and interpret it. And the open source tools that I've seen at this point, again, are kind of what I see is more geared towards indexing signatures or indexing hashes that we can then do exact cryptographic hash lookups or maybe fuzzy hashing lookups. And ultimately, I think there's some other techniques that might be interesting to consider here for malware similarity. So this is where nearest neighbor search comes in, from data mining and machine learning research. And it's a task that basically, given some set X or given our corpus, we want to take our query XQ and basically return the K nearest neighbors. So K could be 5, 10, 25, 100. That's basically picked at query time. But ultimately, we need to come up with these methods of basically use some distance function or distance metric that allows us to quantitatively compare, one sample to the other. So that's nearest neighbor search, and there's a variation of this called approximate nearest neighbor search, which kind of relaxes that threshold of requiring exactness of the neighbors and allows some kind of error threshold basically on our distance function. And really, thinking about this, in just 2 dimensions, if we plot a couple of points, so these could be samples on 2 dimensions here. If we query our red dot, we're looking with nearest neighbor search and k equal 3. We're looking for a system that can retrieve those 3 samples that are in the blue circle and do it really fast. And if we have maybe an approximate version of our nearest neighbor methods, there might be some error bounds that we'll have to be willing to accept, at the trade-off maybe of better query time performance. So in order to do this, so outside of using raw bytes for some of these methods I'll talk about in a bit, we need to come up with a feature representation. And of course, feature engineering is key here. Without having good features, garbage in, garbage out from the model or from whatever system we're building. So it's really important as domain experts really to select features that we extract and then represent in a way that capture those characteristics of the sample. And from a toy kind of perspective here with only 4 features, just to kind of give you a sense, we're dealing with this n-dimensional feature space. And let's say we have 3 samples in this table, x1, x2, and x3. If we have 4 features, maybe just file size, number of exported symbols, and imported DLLs, we can take those continuous values and just represent those as a feature vector, which is really just an array of numerical values. And with this, we can now have a quantitative way to actually compare samples with those values. So distance and similarity are very important for doing nearest neighbor search. And the kind of intuition here is that distance and similarity are very closely related. It's basically just a transformation from one to another. So the farther away we are from some point, the more dissimilar we are. The closer we are in distance, the more similar. So there's many different distance metrics, that have different properties. They're useful for different tasks. There's kind of the standard Euclidean distance. There's string metrics. I heard it mentioned earlier today, but like edit distance or Levenstein distance. There's Hamming distance too, which requires strings to be the exact same length. So there's many different metrics out there that have, again, these axioms and math that allow us to make assumptions and use them in ways to compare these arrays of values. But the one that we're kind of interested in today, that the methods that we'll ultimately use in Rogers is it's the method called Cosine Similarity. And what this does really is take the dot product of the vectors and divides it by the magnitude. So looking at our toy sample here, or our toy sample features, if we take the cosine similarity of x1 and x2, we'll get 0.9944, and with x1 and x3, we'll get 0.9945. And that indicates to us that they're very similar. And the interesting thing here is, again, these are toy features. With cosine similarity, we're ultimately just looking at the direction of the vector. We're not really necessarily interested in the magnitude. So even though the file size is significantly different in this case, we're still going to get a pretty very similar distance or very similar metric back from cosine similarity. And this indicates to us that we need to get different features. This image on the right here is actually a plot of a small data set that I basically have downloaded from this paper called Variant, which is a paper about malware similarity. But this is just projecting a higher dimensional space of these features that are basically implemented in a pipeline in the Rogers tool, and we're plotting only 2 dimensions. So starting at the origin, so basically the center of that chart, we can plot the vector for a particular sample. Again, we're projecting down in 2D just to kind of make sense of it visually. The cosine distance intuitively then is really just the difference between where these angles point. So you can see already there's a lot of vectors that really correspond to a sample that all point in the same direction, and some point in completely opposite directions. So this is really what drives the ability to do nearest neighbor search by giving us some way to actually measure the distance or conversely figure out the similarity between 2 of these vectors. So now it's time to go through a little bit of theory and literature. At a high level, I think nearest neighbor search methods can be grouped into 3 different categories. We can go with the kind of old school space partitioning methods. There's hashing methods, which I think will be more familiar with this group. And then there's graph-based methods, which are kind of more recent and more basically have a lot more moving pieces. So with space partitioning, the idea is that we are taking those vectors and the dimensions they represent and trying to partition them into regions, that we can then use as like a reference or as an index into that particular region. And then we search by that space for nearby neighbors. For hashing, we're taking some input and we're basically mapping it to a bucket, and things that hash to the same bucket are supposed to be similar. And for graph-based methods, we're constructing this basically a proximity graph using certain methods and even methods that have multiple layers of graphs. And we've traversed the graph and basically try to expand nodes or expand the neighbors and find a candidate set of neighbors that we want to pull back and ultimately do comparison on. So these methods, again, aren't specific to the domain of malware similarity. They're very widely used in database systems, information retrieval systems, web applications, and in this case, we're trying to figure out the best one that makes sense for malware data set and doing malware similarity. So with space-based partitioning, KD trees, ball trees, cluster pruning tree are the kind of three that comes to mind. The KD tree and ball tree are actually provided in scikit-learn. It's a Python library for doing machine learning. So these two trees are actually used as kind of lower-level components in a lot of the more complex tasks, such as clustering or classification. And ultimately, what we're doing with any tree method is trying to, again, kind of split our data set into nodes, that best distinguish or best differentiate the data. So specifically with KD tree, which kind of shows a small illustration in Figure 2, is we're taking all of our data sets at the root of our tree. So we're building this tree-like data structure, and we're going to pick a feature that kind of best, in our case, we can pick it randomly or select one that best distinguishes the data in terms of its distribution. We use that feature, and then we split that data set into anything being on the left side of a feature goes down to child A of the tree, and anything that's greater than that feature or equal to that feature goes down to the right side of the tree. So really, in this case, in KD trees, is really just a generalized binary tree that we're constructing and kind of splitting our data into leaves that ultimately we can then go and search through from the top. And there's a lot of ways to construct trees. The cluster pruning tree is interesting as well too. It's more of a randomized approach to doing it. We just select some random number of leaders, that represent like where we're going to split our tree, and then we partition our data set based off of how close all of the other data points are. So again, these space partitioning methods they've been developed a long time ago. They're great for small dimensionalities and smaller data sets, but they start to break down in larger data sets and higher dimensional spaces. So hashing methods are another approach to nearest neighbor search as well too. And hashing methods, we're ultimately taking some hash function and we're mapping an arbitrary input and we're going to map it into a finite output. So cryptographic hashing is, I think, well known, well understood within this group. But there's a lot of other hashing methods actually out there that are categorized as like non-cryptographic, data independent, or data dependent. And these ones are more useful for doing similarity comparison between samples. And the whole idea is that a small change in the input will only result in a small change in the output of the digest. And this allows us to use the messages or the digest messages in either lookup tables or even using them directly to do fast distance comparison. So locality sensitive hashing is one of the more prominent hashing methods. There's a whole group of LSH-based methods that really takes a family of hashing methods that have certain properties about them. And basically use LSH. You take a bunch of different hashing functions that you randomly select most of the time, and then you take your input and you build this k-bit hash code that you concatenate together, and ultimately that represents the bucket that an input or a sample in our case maps into. And hashing functions that are LSH or used in LSH are interesting if you can make certain guarantees around the probability that they hash to the same bucket and that it ensures their similarity. So min hash is one of the earlier LSH methods that effectively estimates Jacquard similarity. So you can use min hash to, instead of doing full pairwise Jacquard similarity, you could do min hash. And of course, other distance metrics as well too have their own LSH implementations. So the one LSH method we'll look at today is actually using cosine. So SSDeep, or context-triggered piecewise hashing, is another very well-known. It's very popular in the industry. VirusTotal supports it. The National Software Reference Library has a data set of all the digests produced. It's great. It has a signature, or has a traditional hash and a rolling hash, and basically constructs this digest whenever the rolling hash encounters a trigger value. You have to do edit distance or Levenstein distance for comparison. There is actually some interesting work that exploits the nature of the digest and provides a way to actually eliminate candidates for search. So Wallace, back in 2015, produced a method that basically takes the chunk size, the block size, and the double block size, and splits it up into this partial index. And that can be done in SQLite, it can be done in memory, and then some more recent work actually did it in Elasticsearch as well too. So that's SSDeep. STHash is another method for similarity comparison that's used within malware similarity. This takes a different approach, and basically on a rolling window of input looks for very statistically improbable features, basically using Shannon entropy. And this ultimately constructs this digest, which is then stuffed into this data structure called a Bloom filter, which is a probabilistic data structure that just allows you to do a quick check to see if something's in a set or not. Unfortunately, with SD-hash, you have to, in order to actually do comparison, you have to do a full intersection of these sequence of Bloom filters, and that makes it pretty expensive to get through. Also, Trend Micro LSH came out a couple years ago. This takes a different approach than SSDeep and SD-hash. It uses Hamming distance to do pairwise, or to do a comparison between the digests. So I haven't seen this yet, but I know that there's a way to kind of leverage some other systems out there that basically build an index for Hamming distance. So the same speed up that the indexed SSDeep gets with partitioning up the digest, you could probably achieve that with TLSH as well too, using this system that index Hamming distances and does a very quick lookup. So that's another method out there. And then LSH forest is another kind of generalized approach that because LSH at times is very difficult to actually find a good number of hashing functions to actually use to guarantee like that probability. It basically makes some thresholds around the accuracy, so this is kind of where we get into the approximate nature of some of these algorithms. The LSH forest overcomes a lot of the kind of hand tuning that needs to be done on a specific data set, and eliminates the need to really deal with like data-dependent parameters, and also has some performance improvements over skewed data as well too. So the LSH forest is actually one of the methods we'll look at today in Rogers. And then finally, the last kind of category of methods is these graph-based methods. And these all kind of, or at least recently, a lot of the methods for graphing nearest neighbor really are based on this premise of neighborhood expansion or neighbor expansion. And this is the idea that a neighbor of a neighbor is also likely to be a neighbor. And in graphs, in certain types of graphs that are constructed in a way that allow you to efficiently traverse them, you can exploit this concept of neighborhood expansion by selecting and enumerating all the nodes that basically are connected to your query node. And this is constructed in offline phase for most of these algorithms, and then ultimately you query based off of a search or a traversal of the graph, and you build up this list of candidate neighbors that you want to do a full comparison, a full distance comparison to. So these early methods, though, have had issues with like local convergence when they're doing their search process at query time, and they also have some of them have expensive graph construction phases as well too. So the interesting method here that we'll look at is this graph method called Hierarchical Navigable Small World, or HNSW. So this uses multiple graphs and constructs layered graphs in a way that you can greedily identify samples that are interesting for comparison. And queries are performed by starting at one of the layers and traversing that layer's graph to a certain point, and then eventually navigating down to the next layer until finally you kind of build this like list of candidate nodes that you want to compare. So HNSW is another method that graph-based method I think has kind of been shown to do pretty well in nearest neighbor search benchmarks. So in summary, again, nearest neighbor search methods, there's a lot. There's many different hashing methods, graph methods, and space partitioning methods. They're useful. Some of them are useful for small dimensionality data sets of small n. Other methods are better suited for the approximate high dimensional spaces and large data sets. So it's difficult to just select one algorithm or one method, and expect it to do well in your data set. This figure 4 here is just one screenshot, one benchmark of one data set on this site called ANN Benchmarks, which is a great site that recently started putting together all these kind of standardized data sets that academics like to use for testing their nearest neighbor search methods. So this is just on the New York Times data set at k equals 100, and there's like at least 15 or 20 different methods that have their own implementations that are being tested here. And the main thing that most of these tests compare is how many queries per second you can get over the recall. So how many relevant results are returned in your query. So what I'm getting at here is that it's hard to really know right away without testing out these methods, and ultimately that's what I hope this tool Rogers allows researchers to do. So related systems that are out there already, or use components of this. So VirusTotal has this structural feature hash that they use in their clustering API. They're pretty slim on the details on their documentation, but I can gather, or they state publicly that they use static features extracted from the binaries. I imagine they're doing some type of distance comparison behind the scenes, or running a clustering algorithm that uses the same ideas here. And this system, virus total cluster endpoint, gives you like the top 200 clusters per day. I saw a couple weeks ago, or last week, where they came out with a new graph interface that I think uses this more extensively. So that's out there. The indexed SSDeep, so that implementation was done by Brian Wallace. It's SSDC, so that uses the speed up at query time to do SSDeep comparison. And then, as I mentioned, there's some later work in 2017, a blog post about basically porting that idea to Elasticsearch as well too. So you can index SSDeep messages or digests in Elasticsearch and use that to look up, what SSDeep digest should be compared to ultimately identify your nearest neighbors. In more of the academic area, there's Bitshred, which does pairwise Jacquard similarity. So it doesn't actually use the min hash. It doesn't use the LSH method for doing a Jacquard similarity estimation. Then there's also this Malware provenance academic system that uses min hash, and that looks at disassembled sample output and does n-grams on the a certain way of, I guess, that they figure out like the blocks of the disassembled sample that they're looking at. So there's SARVAM. So this came out a couple years ago too. So this method takes the raw bytes of a sample and basically uses some concepts from computer vision and converts that to a grayscale image, and then ultimately does distance comparison on the images itself. So they have their own database of these images, and I think they've indexed several million at this point. And I'll give you this interface to search through. And then there's also Malware, which came out in 2011. So this uses a sequence representation, and it's more on the dynamic feature space. And it uses behavior extracted from a variety of sandbox reports. So Cuckoo, I think at the time they were doing it with JoBox. Maybe they're doing more now. But this uses this idea of prototype selection to kind of power their more advanced clustering and classification tasks that Malware provides on dynamic data. And with prototype selection, we're basically looking for some average point to describe a cluster. And then we can use that prototype, or really this centroid, or this average point that we can use as a lookup reference to go to other samples that fall near to that sample in the feature space. So that's really kind of, from my survey, at least, like kind of doing some research out there, trying to find some of these systems that are either available publicly through open source or were published in papers, do this malware similarity or have various components of malware similarity. All of them, of course, had different use cases in mind, and when they designed the systems and the tasks that they were trying to develop were slightly different than what I think this tool Rogers does. So ultimately, I can boil this down, I think, into four different use case, or four different tasks that I think that a tool that does malware similarity using nearest neighbor search methods, what it should do. So number one, we need to extract the feature data. So the raw features, we need to take it out, stuff it somewhere for us. We need to transform that feature data into a representation, so into those vectors, that we can then feed into one of our nearest neighbor search methods. So this is done with a per file type pipeline. We might need to do some dimensionality reduction. Number three, we need to fit all of the methods. So each method that has its own type of construction phase, or might have different requirements for actually building an index. And then finally, and most importantly, we need to have an interface to allow analysts to query the different indices and get back samples that are neighbors, and maybe also return some relevant contextual features as well too. So that's kind of what I put together in this tool called Rogers. So this is a command line application. It's developed in Python 3. It's quite new. I think I've developed it over the past month and a half. So I would definitely appreciate any pull requests on GitHub, which I'll get to in a bit. So this tool uses multiprocessing. It uses a multiprocessing pool to kind of help speed up the feature extraction. There's a protocol buffer definition that helps track the different type of raw feature data that we can extract. And then SQLite right now is being used for a local database to track all of our results and any other metadata that we want to track. Outside of the command line interface, I also, with this talk, and I'll publish on GitHub after this, I have a Jupyter notebook that uses a JavaScript library called Plotly to visualize some of the results from querying our nearest neighbor indices. And at this point right now, so the system implementation, so beyond some of these core use cases, what methods are we looking at right now? So indexed SSDeep, which I've kind of talked about a lot. The cluster pruning method, which randomly selects different leaders and then partitions based off how close the followers are to the leader. The LSH forest, so helping us automatically tune a variety of LSH methods for querying, and then this graph-based method, hierarchical navigable small world, HNSW. So these are 4 methods that I have right now. Methods 2 to 3 are just using other libraries that are out there that are available in either data science Python libraries or in other implementations. The indexed SSDeep is implemented using the SQLite, and that's based off of the original blog post. For feature engineering, I have a simple static feature extraction pipeline that looks at PEs only right now. So it uses the header, pulls out various bits from there, and then also uses all the rules in the Yara rules for project as additional signature-like features, that ultimately give us about 5,000 to 10,000 or so dimensions after we construct this pipeline. From that pipeline, then we have to reduce the dimensionality down to something that these methods can use. So there's a method called latent semantic indexing, which is popular in like document clustering and classification. So this whole pipeline basically follows a suit of that, and ultimately gives us a 512 dimensional feature space to work with whenever we're doing indexing in these methods. So for data, data is hard to come by that's publicly available. So I went with kind of one, an academic data set, and then 2, a data set that I curated from VirusTotal. So first is this variant 2015. So the variant paper came out a while back that basically attempted to kind of standardize a data set around tools that were using doing malware similarity, and they tried to kind of standardize this data set with only 83 samples, and used various methods. I think they compared BitShred, they compared SSDeep, they compared TLSH, and ultimately the data set is there and it's well understood, but it really doesn't give us enough samples to kind of test for this use case of nearest neighbor search. So in January, I pulled down on one day 27,000 samples or so from the VT cluster API, representing about 15 clusters. And this ultimately consists of about like 1,500 samples per class. So these 2 data sets are used in the tool. I have the hashes all published so you can reproduce everything yourself if you're interested. And ultimately, for precision metrics, so comparing the benchmarking, basically, these methods, we're looking at a method called precision at K. So this is a performance metric that's used in information retrieval systems that basically takes the number of relevant documents returned in a query over the number of retrieved documents. And in this case, we're using the class labels for each of these data sets to basically determine like what's relevant. So we would expect, again, this is very dependent on your feature engineering, but we would expect to see a method bring back high precision and be consistent across all the methods, and that indicates to us that it's doing a good job at finding the nearest neighbors, the true nearest neighbors. So if you look at this bottom table, at the very bottom, there's a brute force method. So I did do the brute force kind of linear comparison of all samples, and this is effectively like the baseline. So at a minimum, if we just did a brute force comparison of our query sample to all the samples that are indexed, the brute force method gives us back the precision values at various levels of K. So overall, LSH forest pretty much beat out everything. However, parameter tuning is pretty a significant thing here. So what I did for parameters for selecting, like basically how to tune each of these algorithms to be specific to the data set, is I went on that ANN benchmark site and basically picked out the top parameters that gave me like really good, or gave the data sets that ANN benchmarks produced good results on. So I tried to kind of pick, I tried to pick from more of an expert perspective from the data science perspective, like what I thought would be good parameters. But certainly there's methods here where we can actually do parameter optimization on each method individually and potentially get better results. And that's kind of one of the takeaways I have, for kind of future work on benchmarking. So again, LSH here, from the data, at least from our experiments, LSH forest really gives us that best precision, in terms of, again, returning the most relevant documents based off of their label, what group or what class they're associated in our data sets. LSH forest does the best. So now I think I sufficiently prayed enough to the demo gods, and I have this Jupyter notebook, which I'll also publish on GitHub for you to kind of reproduce. But pretty much this Jupyter notebook just, one, demonstrates some of the command line interfaces, or the command line arguments and parameters that you could feed into the tool. So we're actually running Rogers from the command line here, so you could just run it and kind of get all the flags, of course. The interesting ones are in this index command. So that allows you to do that extraction, transformation, fitting of the various methods, and also querying of the methods. You could extract your own directory of samples. So if you have samples that you pull down from some incident or from another system and you get them locally, you can run this tool on it and basically extract everything and make it available to the either for indexing or for querying. You can fit each method individually, and then more interestingly, you can actually query a method. So this one we're querying the LSH forest for this particular sample, and getting back the by default 5 nearest neighbors. So you would see the query hash, the neighbor hash that comes back, and then again going back to that slide on cosine similarity, the actual similarity that our index has for these 2 particular samples. So you can query all these different methods. Here again, here's kind of a summary of the data set, and getting into like more of a kind of visualization perspective, I guess, if you want to see the raw features. So this is the protobuf definition that breaks out static, dynamic, and contextual features. And just for one sample here, we can see all of the feature names, what modality they are, if it's an integer value or a float value or a Boolean value. So as analysts, you could dig into this and see like the raw data, that corresponds to one n-dimensional vector, right, that represents this. So it's all the raw data is there. Sorry, question?
Yeah, those imports, kernel 32 DLL.
Yeah, so sorry, this is pending the import DLL with the actual function.
If it's packed.
Yeah. So again, it all depends on the features. If it's packed, all the packed samples for various packers are all going to cluster, are all going to come together whenever you query them. So yeah, I mean, definitely. This talk isn't about feature engineering, but more about like the methods that you could use. Rogers has an extensible protobuf message or protobuf definition that I think you could figure out ways to take in your dynamic features that you have in Cuckoo and basically extend it like that. So for contextual features, this is where I take kind of at liberty. I take the Yara rule signatures that are matched, and then also like whatever label data that you have. So you can append contextual features as well too with samples. So this is just the contextual features for one particular sample. And then, again, under the hood, the CLI does all this for us, but we can load up each of the indexes that we have, and then basically do these plots using Plotly. So here's an example here of using the LSH index, querying one sample, asking for the 5 nearest neighbors, and then we're not going to do neighborhood expansion, which I'll talk about that again briefly. But if we run this, basically just get back this force-directed graph. So this is taking all the points. So here's our query point in the center. We can see some of the contextual data and the signatures that are associated with it. The edges between the nodes represent the similarity. And here on the outside, basically from the outskirts of our node here, are all the 5 nearest neighbors. And just kind of at a glance here, gut checking us on the features that we selected, in this case, this pipeline that I created, we can see that group 1, group 1, group 1, group 1. So this is from that variant data set, 85 samples or so. If we go further, we can use other, so we can query one of the other indices. And in this case, I guess it's hard to kind of see side by side, but this is actually giving us back different samples with different similarities. So each method, basically, again, this all comes down to which method is the best for our data set, which method exploits certain properties of the features or the representation. And in this case, this is the graph-based method. This is, well, you have to trust me on this, but we can look at the Jupyter Notebook after. It's actually returning different samples than that original query. And this goes back to the experiments showing that LSH forest, is a pretty decent method for doing nearest neighbor search. So we can get even more samples in our query, and in this case, these are all the variant seed samples. So this is the 85 samples. Our whole index that we have right now, which is both I should have mentioned this earlier, it's both the variant samples and the virus total samples all indexed together. We can do k equals 5, and then what we do is return all the results, all the 5 nearest neighbors for each of the samples, and then basically cluster them all together. And again, this is all based off this force-directed layout in Plotly, which takes into account like the using the similarity as like the edge weight. So it helps us kind of blow out, push away nodes that are more, or I should say, are dissimilar to one another, and bring nodes closer that are similar. Just visually we can easily kind of jump into samples that are that should be similar to each other. So again, here's actually again this variant group 5. We can see the similarity is 1, so it has a vector. Again, since this is cosine, this is telling us that vector is in the exact same direction compared to this other sample right here. Around here, here's another group 5. So at least this interface gives us a way to take all the results of this tool and visualize it in a way that could be interpreted and basically check if the similarity actually corresponds to the understanding of the features that are used. So again, it all comes down. We're not learning any features. We're not doing any feature representation beyond like some of the standard methods. But we can use that as is and just basically get some interesting results on the static data. So we can use that idea of neighborhood expansion and include the neighbors. So we query our data set, or we query our index with the variant seed samples, and then we also return back any samples that they have been matched with, and also query the index with those samples as well too. So that allows us to basically walk out even further into our index and bring back even more results. So here's another example here. So these actually don't have any labels. But what this indicates to us is that the neighbors that come back have the same, basically using the features that we've selected, they have similarities. And we can use that to help, again, figure out like what context is associated with some unknown sample that we don't have in our index. And from there, we have a little bit of contextual data to start our analysis, or to figure out like what to do next in terms of routing it to a tool or another system, or going further and doing reverse engineering. And this is pretty much more of the same. So for SS-Deep, the SS-Deep, if you recall back from the experimental results, it had the worst precision. So it didn't really return any results on some of the queries. Here's like that being plotted. So a takeaway from this is that SS-Deep, although popular and although supported in services like VirusTotal, if you control your binaries, like there's better methods, there's better representations that you can pick, to do similarity comparison. Cool. So in closing, I want to stress again that feature engineering, is very key to how well these nearest neighbor search methods do. If you don't have good features, or you pick features that only, basically can be avoided or look identical by using packers or cryptors, it's not going to work. So that's why, looking beyond just like static features and including dynamic features as well too, or what we call different modalities. It'd be interesting to use in combination with a tool like Rogers. And feature selection and learning representations, some of the more advanced methods that could also help identify better features that could be used in this tool as well. For experiments, the experimental results are really just based off this data set that I've collected. So we could make assumptions around like how well this data or how well the methods will scale out. But it would be great to have more benchmarks. And as I mentioned, parameter optimization, each of the methods has to be tuned, with different parameters to make it either better at recall or better at precision. So that could be explored better. And then for use cases, all the samples that have been indexed are only, it's only malware at this point, but you could also use this to index like benign samples as well too, and see if like your query comes back with, the nearest neighbors are both benign and malicious, that could lead to other questions. And then finally, partial fit. So doing updates, basically insertions to the index. Right now, the tool only supports offline fitting. So your whole data set is indexed each time in the methods. Some of them have, some of the methods like LSH Forest have support for partial fits. And with that, any questions at all?
If you took two samples, Rad A and Rad B, and you packed them both with Armadillo, would they come out right beside each other in this?
Yep.
They would?
So again, full disclosure about the feature engineering, like it's just basic static feature extraction. If we look actually, so the variant data set, there's several groups here that use Armadillo as packers. So group 1, it is a different RAD, or I think there's a couple Trojans in there. There's some pups and stuff. I'm sorry.
Those backticks?
There we go. Yeah, marked down. So For this data set, it makes sense that group 1 all comes back together, but you can see armadillo is used in all these different groups, other than this group 5. If you're only looking at static features and you were building your index on just static features, your results would look more like packers that basically come back or are very close together in the feature space.
Okay.
Thank you. This is the first conference I did this talk at, so any feedback would be appreciated.
A clarification, it's partly because I can't hear you that well with the...
Sorry.
Just a clarification based upon the previous question. So sample A, sample B, both packed with the same packers, those get spit out adjacent to each other. However, sample A unpacked, sample B packed, presumably that those do not come up next to each other. Are you considering putting in, correct me if I'm wrong on that, but presumably if you have a packed and an unpacked sample, are you considering normalization either to try and unpack if it's like UPX or Armadillo? Okay, so that's really data sanitization.
Again, this tool was developed with love over the past month, over Christmas, and over New Year's. It doesn't have stuff like that. Doing that stuff's pretty cool, but that sounds more like products. So as far as like how to overcome stuff like that, I think using a tool like Rogers, you could think of adding in dynamic features, with this protobuf definition here. So there is a way to take, output from Cuckoo and use the same kind of approach. Again, this latent semantic indexing, which again is a very simple method that is relevant for document classification and clustering. It would be pretty cool, and you could do that if you wanted to. And that I think would help accommodate some of the issues with packers, encryptors all looking, the same.
The one thing that as soon as I see this, I go back to some of the data from Cuckoo, and one of the things that makes it really easy to tell what family of malware it is how many times certain APIs were called from the parent binary. And just the amount of API calls, plus or minus, if you did some of this distance mapping on that, you'd have the families clear as day.
So I think, maybe doing something with Phoenix, maybe not in MongoDB, but,
Thanks a lot.
Well, thank you.
This was awesome.